So welcome back. Today's lesson is chapter 11, the deaths of stars. Last time we took a look at the formation and the internal structure of stars, kind of how they're born, how they live their lives. So now we're at the point where we are going to look at the death throes, the various death throes of our stars. Our What Are We summary is probably my favorite, but it is we are stardust. Stars have died so that we may live. And it's a very true concept, in fact, that we are stardust. The molecules that make up our body, the iron in our blood, and the calcium in our bones all came from star deaths. So we do owe our lives to stardust. So I kind of like that one. That's my favorite, I think. So chapter 11, we do want to get started with that. It does take us through quite a few different death stars, and these are really based on the various masses. I do have a handout for you that you need to get a copy of. I'm not sure that I have this on Blackboard, but we'll need to make sure we get this to you. It's just a nice summary that summarizes really all of the star categories that we're going to be looking at, the various leftover remnants and objects from our star deaths. But just to briefly look at it, you might not be able to see it really all that well from the camera. But if we look at the very low mass stars, which would be at this end over here, very low mass, 0.013 to 0.08 solar masses. Remember, 0.08 solar masses, that's sort of our lower limit of our stars. And so if it's less than that, we don't really call them stars, but they are what we gave you that term brown dwarfs last time. We mentioned the brown dwarfs, so fairly massive, but yet not really very luminous at all. So they're even beyond the M stars, the L and the T that they added. But if we look at our low mass stars, so 0.08 solar masses, that magic number, to 0.4 solar masses, you can't see it too well, but the method of energy transport in those really low mass stars is completely convective. So that's an interesting thing that's happening in these very low mass stars. They don't have a lot of weight to kind of support, so that they end up having a completely convective all of their shells of the stars. So that's an important difference there. And then we have stars that are from 0.4 to 2 solar masses, let's say. Something like the sun, which is 1 solar mass. Remember that these stars have a radiative zone towards their interiors, and then also a convective zone as far as energy transport goes. So 2 different regions, right? Radiative, and then the most outer there with the convective zone. So these can become what we call red giants, swelling into the red giants. Remember, coming off the main sequence, those red giants were in the upper right-hand corner of our Hertzsprung-Russell diagram. And so they can kind of get a helium flash, we call it, and create these planetary nebula. And then some of their remnants are on the order of what we call white dwarfs. We've mentioned the white dwarfs also on the Hertzsprung-Russell diagram. We'll take a look at those. And then here we have a 2 to 4 solar mass, which again, it's got a convective zone way in the outer portion and a radiative zone in the interior as well. So that's sort of these 2 different categories, but some of the same or similar product or remnant objects. And then over here, where we've got very massive, so greater than 4 solar masses, would be this variety. Definitely having a radiative zone here, also a radiative zone on the outer portion, and convective zone, just way out on the very edge of it. But these would be our supergiant categories. And these end in supernova explosions. And depending on what's left over, so sort of the core after the supernova explosion, kind of what the core mass is of that, we can separate into a couple very compact objects. One category known as neutron stars, or these pulsars, and the other variety we call black holes, so stellar black holes in this variety. And so as you can see, it's really set up with what their beginning mass is, and that kind of dictates how long they're on the main sequence. We kind of learned that last lesson. And what type of death row they're going to go through. And so this is just a synopsis. It's not in your book, of a little handout. It just summarizes what we're going to be talking about today. So I'd like for you to kind of have that as a summary. Okay, so deaths of stars. So gravity is patient. Remember how we said gravity always wins in the end, and it is so patient that eventually it will kill our stars. So they kind of start off talking about a nova, how every now and then you can see what we call kind of a new star in the sky. It gets a little brighter, something like that, but a nova is really produced by an eruption around a stellar remnant. So it's a dead star that just activates a little bit around the remnant there. So that's what a nova is. A supernova is a particularly luminous and long-lasting nova, so much larger in variety, and it's caused by the violent explosion of a star. So a violent death of a star, explosive star. So those would be some of the more massive stars would die in that manner. But we have learned in the last lesson that stars kind of resist their own gravity, that inward pull of gravity. They resist that by generating their own nuclear fusion energy, and so creating that pressure and that internal heat that causes sort of the outward expansion. So that nice hydrostatic equilibrium that's occurring in the nuclear fusion generation, all kind of opposing then that inward pull of gravity. So they are kind of doing their normal star stuff, keeping their interiors nice and hot, and giving that nice balance between the high pressure and the gravity. It prevents the star from collapsing. But recall last time I did say that these stars are finite. They only have so much hydrogen that they can fuse into helium, so limited fuel. And when they do start to run out of their fuel, interesting things start to happen in the various shells. Remember the concentric shells of our stars, and different things can be happening in each of those shells we're going to see. But eventually, gravity is going to win out, and it will end up collapsing down on your star. So gravity does win, and the star does die and goes through various death kind of throes. And the mass of the star is critical. So you just saw that summary figure that I showed you, that really determining its fate was based on what its beginning mass of the star was. And so massive stars, if you recall, are going to use up their fuel very quickly. And so those are shorter lived, right? I mean, we're still talking millions, a million to 100 million years, but much faster than a lower mass star, right? So main sequence stars generate their energy by nuclear fusion, and we're getting the hydrogen and forming helium, right? So combining the hydrogen to make helium, that's sort of the definition of what a star does. And it's going to spend its time on the main sequence. About 90% of its life is going to be on the main sequence doing its energy generating type of a star. But when that hydrogen becomes exhausted, the star is going to begin to actually evolve rapidly. We can get things that they are going to swell into what we call the giant stage. So they've moved off of the main sequence. If you remember, we've got giants and supergiants out there. But it begins to fuse the helium. Okay, so it's sort of this helium ash core okay, is accumulating at the center of the star as hydrogen's fusing to helium. It kind of creates this ash core of helium. Well, if temperatures get hot enough, then they can actually begin to fuse the helium into these heavier elements. We'll have carbon next and some oxygen coming along, kind of thing. So it can't really stay in that giant stage for very long, maybe 10% of its life, and then it's going to have to die. So the giant stage is kind of the first step into the final kind of death throw there of a star. Okay, so nuclear reactions in main sequence core is producing that helium that they're talking about. So in order to get helium to ignite, you've got to get your temperatures up to 100 million Kelvin. Remember the proton-proton chain, we just needed 10 million, 10 million Kelvin to get that one, and the CNO, or the carbon, nitrogen, oxygen cycle, 16 million, okay, to get those to fuse hydrogen to helium. Well, now if we got all this ash of helium, we really need a hot star, 100 million Kelvin, okay. No main sequence star has a core that can get that hot, okay. So helium's just going to accumulate in the star's center, kind of like this ashy fireplace sort of thing. But initially that helium has no effect on the star, but the star's ability to generate nuclear energy becomes reduced, right? It doesn't have as much hydrogen in the core in there. So the core helium can't generate nuclear energy, but yet it can get hot. Okay, it's not producing energy yet. It's not hot enough for it, but it can grow hotter from the gravitational kind of collapse that's occurring. So it can grow hotter, and it is kind of contracting, right? Because it's not resisting that outward pressure very well to the gravitational energy. So its temperature can rise, and it can get to a point to be, 10 million Kelvin, where it will start to ignite a shell. Remember how the star has several layers to it? Well, that rising temperature can heat up a little bit of unprocessed hydrogen just in a shell right outside of the core in there, okay? So that hydrogen was never previously hot enough to fuse. So now here we've got this helium ash core and an outer shell where we're getting hydrogen fusion to happen. So nuclear fusion is occurring in a little shell outside of that, okay? And so I think there'll be a nice picture. Here we go. So here, the core of the star, the center of the star, and we've got this ashy helium core, okay? Hydrogen's already gone to helium, and it's not hot enough there for the helium to ignite, but yet it does get hotter so that we can now ignite what we call this hydrogen fusion shell. Okay, so hydrogen fusion shell just outside of the core sort of thing is going on. So that's going to produce a flood of energy from that hydrogen fusion shell that's going to push outward. So now we're getting some pressure pushing outward. This heats the outer layers of the star, forcing them to expand dramatically. Okay, so we're kind of calling this going through a giant sort of phase. And expansion of the star to the giant or even the supergiant, it starts to cool the star's outer layers just a little bit. So when it does that, the stars are moving up a little bit on our Hertzsprung-Russell diagram here, and a little bit to the right. So the cooler temperatures are to the right. And so you're getting a little bit of cooling off occurring. So here's normal main sequence, hydrogen to helium in the core. Here's where we're starting to go through the giant phase. Now we've got the helium, inert helium in the core, and that little hydrogen fusion cell. I realize you probably can't see that too well, but you have these PowerPoints to look at. And so you're going through this sort of giant phase in there, and that's the beginnings of your death throes. So the most massive stars end up becoming supergiants, right? So all based kind of on their beginning masses in there. So we are getting some things to start happening that are making some changes in those shells. That's creating sort of an expansion into this giant phase in there. Okay, so it does change the star's kind of structure in there. Now, if we can kind of continue on, where we can finally get it heated up enough, okay? So we got that giant fusing hydrogen in a shell, and then you've got that inner helium core. But when that core finally reaches 100 million Kelvin, which it will continue to heat up because gravity's contracting in on it, the helium can begin fusing and make the next heavier element, carbon. So now we got a lot of different things going on. We've got now helium fusing to carbon in the core in there, and then you start, so helium's fusing in the core, and you've got a hydrogen shell fusion surrounding that, and you just start getting variations of those layers with different kind of fusions going on. So energy's flowing out from the core, which kind of halts that contraction. We've got some new pressure in there, but at the same time, that outer part, the star's envelope, okay, contracts and grows even hotter. So again, different things happening within different layers in our stars. So it is a good idea to think of it as these concentric kind of layers. So the point representing the star in our diagram, okay, would move down just a little bit to lower luminosities, move to the left a little bit, higher temperatures. So it is kind of moving a little bit as you kind of see it. Here's our main sequence, and then it's kind of moving to the right. Okay, now we're going back to the left a little bit. So it does move. The point that represents the star on here can move in the HR diagram. So moving off of the main sequence, okay, it's known as the horizontal branch, okay? And so you can get, depending on kind of your size, your beginning mass, of whether or not this is going to be a red giant or a yellow giant. So there's a little distinction kind of between that, and that's what they're kind of taking us through there. But it's moving kind of back and forth through this loop, whether it's a red giant or a yellow giant sort of thing, but going through various fusions in the different shells, okay, in there. I think they're kind of doing some, what's the evidence for this? And so we look at star clusters. So they've done some studies with star clusters, and there's a couple types of star clusters that they take a look at that can help us kind of gauge the age or what stage the cluster is in. And since we talked about these sort of nurseries where star formation occurs, the idea is that these stars are probably very close to where they were born. And so these star clusters, you can probably put an age on the entire cluster, the composition of your stars, because of the clusters. They all formed in sort of that same dense molecular cloud. So they will have some similarities as far as their age and their composition goes. But a couple kinds of clusters. Off over here, you see they're kind of spaced out fairly sparsely. So 100 to maybe 1,000 stars in these clusters we call open clusters is one type, an open cluster. In about a region of 25 parsecs in diameter. And these have a very open and transparent kind of look. So not real dense like this one. So kind of transparent, open. Typically these stars are quite young in a open cluster. And I know we haven't gotten to our galaxy information, but these would be more in the disk region of a galaxy. You would find an open star cluster. On the right here, we have what we call a globular cluster. These are much more densely packed, anywhere from, could be like up to 100,000 stars in this one. Well, 100,000 to 1,000,000 stars, so very densely packed in there, as you can see, in contrast to the open cluster. And these stars are generally old stars, and in a galaxy they would be kind of confined to the spherical component of the galaxy, and we will get to that again when we get to our galaxy unit. But open clusters and globular clusters are some clusters of stars that they do study, and looking at the way that the stars evolve over time. But you can kind of judge the age of a star cluster by looking at its turnoff point, where it's turning off on the Hertzsprung-Russell diagram, okay, where they're turning off, going to the right to become giants, like we were looking at there. And so you can look at the life expectancy of those stars at that turnoff point. So they're, turnoff point right there. And gauge kind of what the age of your star cluster might be. And so that's one way. It equals the star cluster's age, right? You can estimate the age of the star cluster by observing the distribution, okay, of the points that represent the stars, right, on the HR diagram. So we have lower mass stars. They're still on the main sequence, right? Those live longer. So you're not seeing a whole lot of the most massive stars, right? They've already lived their lives and they've moved off of the main sequence, right? So they've already died. But here we're getting just a little few that are in the giant stage, okay? And so from this, just studying this, we can kind of gauge the age of our star clusters. I think they're going to take you through like some actual ones that they've studied, okay, and where they're estimating ages just because of what they're seeing, on the turnoff point, or that horizontal branch there for different ages. Okay. Just a little bit of evidence for the evolution. That can give you the age of the stars on there. Okay, so we want to look at the various, kind of like our summary chart was put together, what's happening in the deaths of low mass stars. So I did mention from our chart there that these are completely convective. So they don't have a radiative zone in there, but they're completely convective throughout. So they behave just a little bit different. They're not going to create the helium kind of ash core, right? Because they're completely convective all the way from their cores to their outer layers, where they can tap into the fresh hydrogen, right, through there. So low mass stars, very little gravitational energy, right? So when they contract, they can't get all that hot, but that does limit the fuel that they can ignite. So the protostar is less massive than that 0.08 solar masses, right? Could not get hot enough to even ignite the hydrogen at all, so they can become stars. But we want to look at the ones that are over that limit, that lower limit of 0.08 solar masses, but no more than 4 solar masses with these low mass stars here. So no more than like 4 times the mass of the sun would be kind of in our category here. And so they're kind of separating those to the very low mass red dwarfs, right? And then kind of the medium mass stars like the sun, okay? A difference between these two groups, and it's what's going on with the extent of convection in the centers, okay? And I mentioned the very low mass ones are completely convective. Your medium mass stars like the sun have a radiative zone, and then the outer layers are convective. And so there's a big difference right there between those two groups. So your red dwarfs are very much less massive than about 0.4 solar masses. And so having very small masses, they have very little weight to support. So of course their pressure thermostat, that temperature thermostat, is set very low. They can just consume their fuel, their hydrogen fuel, very slowly, right? These have very long lives. In fact, to the point, I think they'll say it somewhere down the line here, and I think I mentioned it last time, that every red dwarf that's ever been born is still alive. They haven't died yet because, 56 billion years of a life expectancy in the universe, we'll find it's not even more than 4 billion years old. So none of those have even died. But they are stirred by the circulating currents of hot rising gas and cool sinking gas, right? So convection is what they're talking about. So the hydrogen is consumed kind of uniformly throughout with these. So it's not limited to fusion in the core like our other stars are. So it can use that all, it's got all manner of hydrogen to kind of use. It's not limited to the interior. And it's a very prolonged life on the main sequence for our very low mass stars. It's, center would never get hot enough to where it could ignite sort of a hydrogen shell sort of thing, or even fuse helium for that matter. So these don't become giants, right? So mixed by convection, cannot develop an inert core of helium, like I was just saying. And so, it can't get surrounded by unprocessed hydrogen, so it's not going to swell into a giant phase for these. So really, we're thinking that not a single red dwarf has died of old age anywhere in the universe. So every red dwarf that's ever been born is still glowing today because they just consume their fuel so slowly. On that. So now, stars like the sun, massive like the sun, a 1 solar mass to a 4 solar mass, these can ignite a hydrogen fusion shell. So you get that inert helium at the core and ignite a hydrogen fusion shell, right? They can become giants, okay? And if they contain less than 4 solar masses, they cannot get hot enough to go ahead and ignite their helium in their cores and become carbon. They can't do that though. That would be the next fuel after helium. Okay, so they can't do that one. But there are 2 key evolutions of these sun-like kind of stars. That lack of complete mixing, right? So we don't have the complete convection going on, unlike a red dwarf star. Because they're not completely convective. They've got the radiative and then the convective zones in them. But that mass loss, so the helium ash is accumulating in their core, surrounded by unprocessed hydrogen. The core is going to contract, and then that unprocessed hydrogen around it's going to ignite a shell. It's going to create it to swell into a giant. And when the helium core kind of finally ignites, the star is called what we call a yellow giant. So a little distinction kind of between those there. And that's going to cause that core now to fill up with carbon ash. So carbon ash igniting, the helium, and then you've got the hydrogen around that. But for this medium mass or sun-like stars, that carbon ash core, they say carbon and oxygen, ash core is sort of the end range for the fusion of medium mass kind of stars. That's the end for them. Because their masses are too low, we're not going to be able to get their temperatures hot enough for the carbon fusion, which is onwards of like 1 billion Kelvin, so outrageously hot. They're just not large enough to get their interiors that hot. The gas, as they're becoming these giants, the gas gets expelled from that, and it's visible kind of evidence that the stars are going through this kind of death throw kind of stage and do die this way. We call this planetary nebula, sort of the expelling of the outer layers of gases. Okay, planetary nebula. Here's a picture of the planetary nebula. Just an expelling of the outermost gases of it, and sort of repeated surges of this. But the aging giant expels its outer atmosphere, okay, and those repeating surges. And these are called planetary nebula. So it's not that it's a planet, it's a death throw for a medium mass kind of star. But that's a planetary nebula image, sort of this expulsion of the outermost layer there. Here's another one of that, looking quite beautiful. In there, but nothing to do with the planet, right? But it's ionized gases being expelled by the dying star. This is the ring nebula, they call that one. But planetary nebula, part of becoming the giant and then expelling that outer layer, and they're just kind of taking you through what's happening with that. Okay. So medium mass stars die by ejecting gas into space, and then they are going to contract. Their interiors are going to contract into what we call these white dwarfs. Okay, so on our little table summary there, we did have white dwarfs category in there. And so we were learning that the white dwarfs are kind of the second most common after the red dwarfs. Were more abundant. And the first one that was discovered as a faint companion to the well-known star Sirius, that little, kind of in that binary, we talked about this visual binaries before, and that's the little white dwarf, and sort of this binary companion that it has with its companion star. It's a little white dwarf though, so some evidence of that. But a white dwarf's mass, okay, is 0.98 solar masses. It's pretty small surface area, so it's about the size of the Earth. Earth's pretty big, but we're talking about even larger objects out there. And it's extremely dense, okay? It's really been compacted down, so its volume reveals it's very dense, and basic observations lead to the conclusion that white dwarfs are astonishingly dense. So the normal star is supported by energy flowing out of its core. However, the white dwarf, okay, cannot generate energy by nuclear fusion. So it's exhausted the hydrogen, and it's helium fueled or processed to carbon and oxygen, so it really doesn't have anything to fuse to contradict the outward pressure, to contradict that inward pull of the gravitational pull. So its interior becomes very hot, but not quite hot enough to get that carbon fusion happening. And so the contraction of the white dwarf compresses the gases to very high densities, to the point here it does become very dense, to the point where our electrons in the gas can't get any closer together. So we are so compact in there that it's really being held together by this degenerate electron matter. It's called degenerate matter in there, but the electrons are packed just as close as they can, but they're being repelled, right? Those electrons don't want to fuse together. They're resisting and repelling. So that's called degenerate electron matter in a white dwarf, okay? So that's kind of how it's keeping a balance from gravity's inward pull, this electron degenerate matter, okay, on that. And very hard, right? The pressure in the gas no longer depends on its temperature anymore. So Unlike a normal star, which is supported by the ordinary gas pressure we've been talking about, this one's supported against its own gravity by the resistance to compression of that degenerate electron matter, okay, in there. So electron pressure, we call that. That's a white dwarf, okay? Compact objects, okay? Very compact object. So it's not a true star, as we would say. It's not generating nuclear energy, and it's almost completely degenerate matter. It does have a very thin layer of gas on its outermost layer that every now and then can flare a little bit. But its future is very bleak. Over time, its temperature is going to gradually fall. It can't shrink any smaller though because of the degenerate electron. They can't get any closer together. And so the heat's just going to continue to flow out into space over time, and so it'll end up getting cooling off and getting dimmer and fainter, moving down and to the right on our Hertzsprung-Russell diagram. Okay, so yeah, those are just going to kind of end that way with the white dwarf. But some things can happen here, kind of about the white dwarfs. So right here, where it's saying the Chandrasekhar limit, we've actually heard this gentleman's name, might have been way back in chapter 4, Subramanian Chandrasekhar. And he did a lot of theoretical type of astronomy, and he came up with a calculation of a white dwarf that would be called a limit here. So unless it gets rid of the extra mass in some way, a star more massive than 1.4, that's the magic number, 1.4, could not become a white dwarf, okay, because the white dwarf can't hold that unless somehow it got rid of that extra mass in there. Now, can stars lose substantial amounts of mass? Well, they do think so, because a lot of them are in these binary companions where it could lose some of its solar mass in there. So, yeah, they do think that sometimes that could sort of be transferred to its companion. All right. So astronomy is about you. We've been dealing with the deaths of, so far, medium mass stars, and kind of what that's going to do to the Earth, the future of the Earth. So it'll swell into a giant. Well, the planets are going to be in the way of that giant phase and the expelling of the planetary nebula, and will probably, its core will kind of collapse into a white dwarf, and that will certainly spell the end of the Earth. But again, the models are showing that we have a good probably 5 to 6 billion years. So our star's the middle-aged in there. It's got another 5 billion years where it's going to exhaust the hydrogen in its core, and then sort of burning a hydrogen shell sort of thing, swelling into a red giant. So we've got some time in here to sort of get this all figured out. But yeah, so it's definitely going to become more luminous and then kind of vaporize the Earth as you go, as it swells into its giant phase. So yeah, kind of a bleak thing there, but right, and just saying your atoms will be part of that nebula that it expels. And then the Earth, yeah, and so this will all go into sort of the gas and dust, interstellar medium, and who knows, a new star could be created as the cycle kind of continues in there. So yeah, we are kind of stardust is what they're, what are we theme in there. But if the white dwarf remnant sun becomes hot enough, it could ionize and expel some kind of gas in the planetary nebula, and you will be lit up, is what they're saying there. So depending on if that happens. So Okay, so a little with the white dwarf, a very compact object with a Chandrasekhar limit of that 1.4 limit. That's all the mass, you know, it could potentially withhold and still be a white dwarf in there. Okay, let's see, active research on that. So binary system, so really we're kind of looking at these pairs of stars in there, which we said about half the stars do have a companion, but certainly the sun does not have a binary companion, right? But the sun's definitely not massive enough to die in the supernova, a violent death of what most massive stars will do. But they do look at these binary systems. Each star can kind of evolve on its own. It's a matter of distance between them. So if one star can swell into a giant and not disturb its neighbor or its companion, then you know they won't really be disturbing one another. It's when they're close enough, so about 0.1 AU, close enough to each other that, yeah, when one goes through its death throw and swells into a giant, its companion can suffer in a variety of ways. And so here they're showing us sort of the star A and star B that are in this companion orbiting again around the center of mass. And if you remember, the more massive star is going to be closest to the center of mass. And here's our smaller one that would be whipping around, you know, out the farthest away from the center of mass. But we have star A and star B. Clearly, star B is more massive than star A, so they'll have, you know, varying evolution. So this gravitational field of the two stars here, okay, combined with the rotation of the binary system, kind of gives us this dumbbell-shaped volume, okay, that's called the Roche lobes, okay, around the pair of the stars. And inside the Roche lobes, okay, it's gravitationally bound to the stars, okay, in here. But matter outside the lobe can be transferred from one star to another, so some of that can be transferred. But if it gets outside of the Roche lobe, that can be lost completely from the system. But if they're close enough together, okay, they can interfere with the evolution of the other stars within that Roche kind of limit or lobe in there. Okay. But if it's you know, far enough away and gets out of that Roche lobe, then it's no longer gravitationally bound and it'll just go off. Okay, and not get transferred directly to the other star. But we can start to accumulate. Okay, so here we have star B in its evolution becoming a giant, and it can lose sort of a little bit of mass to star A. So it's giving a little bit of that mass to star A. Star A is starting to gain a little bit more mass here. So now star A has become a giant, okay? And the remnant here of the mass back over here becomes a white dwarf in star B. So they can affect one another's evolution if they're in these binary kind of companions together orbiting one another, and that's certainly what we're seeing there, getting a little bit of that mass transferred from one star to another. Okay. So in an accretion disk kind of around it. So the gas in the disk is growing very, very hot, as we can see here, going around it. This is around the white dwarf, okay? And it eventually is going to fall in on that star. Very compact object, the white dwarf there. And so it comes to be very compressed, gets very hot, can exceed, you know, 1,000,000 Kelvin in here and start producing some X-rays coming off of that. And so the matter accumulating around the white dwarf can cause a violent explosion known as a nova coming off of the white dwarf, okay, there. But yeah, this can happen if it's gaining a little bit of mass onto that white dwarf. It can flare up and produce some X-rays in there. So they can really affect each other. So a nova is really an old star kind of flaring up. It's not really a new star like you would think nova would mean new, but it's an old star kind of flaring up. So when mass is transferring from a normal star into the accretion disks around the white dwarf, you can get that flare up, that nova to happen. Okay, but it's involving a normal star and a white dwarf. Okay, in a close binary system, a nova is. Okay, let's see. And they're just showing us some beautiful pictures of, you know, various nova. So here's our death of our massive stars. So now we're starting to get greater than 4 solar masses for our massive stars. So they live spectacular lives, and these are the ones that are going to have the violent explosions. So it's not going to be the red giant thing, the white dwarf kind of thing. These are going to have some violent explosions, massive stars. So once the gas in the core of the massive star is fusing its nuclear fuel to iron. So iron's like the dead end kind of thing. Stars cannot get hot enough to fuse iron, right? So iron's kind of their last element. But let's take a look here in our massive stars. So they're going along, beginning like the lower mass ones. So they're consuming their hydrogen in their core, right? Igniting a hydrogen shell. And then they're becoming giants, or maybe supergiants, but the cores can contract and they can fuse helium, first in the core, and then in a shell, and then you're getting the carbon in the oxygen core, right? So now we're getting that to occur. And so when they get up to 1 billion Kelvin, now their carbon can go ahead and fuse. So carbon fusion, and it's producing oxygen and neon, so you're getting heavier and heavier elements that are getting cooked up in these very massive stars as they're entering their death throes. So we're getting heavier elements being made in stars, okay? But as soon as the carbon is exhausted in the core contracts, and then we get a carbon shell to ignite. So I think there's a nice picture, but just look at all the layers that we're seeing in here, where you've got, at the end of it all, you've got iron in the core, so most tightly bound element, right? We remember that from another lesson. The iron in the core, surrounded by silicon, another atom, then oxygen, then neon, then carbon, then helium, and then the outermost has got a hydrogen fusion cell. So many things happening in this star, in each of those different concentric layers or shells within our stars. So many things happening in here. Okay, so higher temperatures, then yeah, you get your silicon to fuse to iron, but iron is the end of the road, and things are going to start happening extremely rapidly for our stars. So the amount of energy released decreases as the mass and the types of the atoms involved increases. So to support its weight, the star must fuse the oxygen much faster than it fuses its hydrogen. And I mean, it just starts to go very rapidly towards the end. So this is sort of, this actually should be a table 11.1 in there. But the fuel, the different fuels, and the amount of time that it takes to go through that, and so the percentage of time of the life of the star that is using that fuel, that's what this table is telling us. So hydrogen, about 7 million years to go through that. So about 93% of its life, it's doing the normal hydrogen fusion thing. 500,000 years for the helium that it has, so a lesser percent. Now, look when we get to carbon. Carbon, it can go through that in 600 years. oxygen in a half a year, so things are going rapid now, and silicon in 1 day. Very, very fast. Things are going to go very rapidly for this star towards its final death. But that core of iron, that inner core of iron, is the end of the road for these massive, massive stars, okay? They're going to, because iron is like the most tightly bound here, is what it's saying on this little chart here. So only when the less tightly bound nuclei combine to more tightly bound nucleus, are you going to release energy. So once it's gone and converted to iron in here, there are no further reactions that can release energy. So you're not getting any outward pressure happening at the core. The core is dead. It's a dead end for the evolution of our very massive stars here. Okay, and that's going to go pretty rapid there. Okay, so the collapse of the giant star's core after iron fusion so rapidly, okay, that's going to happen, and 99% of that energy is in neutrinos, and so they do try to detect the neutrinos. I think we talked about that last time, so evidence of some of that. But models predict that collapsing core of the star must either quickly become one of two of these compact objects, the neutron star or a black hole, okay? And the envelope gets blasted outward, so in an explosion sort of thing. So the inward collapse can be kind of thought of as sort of a traffic jam sort of thing. You get the collapse of the innermost part of the degenerate core, right? And it allows the rest of the core to fall inward sort of thing. And then that sends a shock wave back outward. And so it's sort of exploding apart, the outer part. You are getting collapsing happening, but yet the shock wave is sending out and driving out the rest of it and just blowing and blasting your star apart in a supernova explosion, we call that. And yeah, these are kind of rare, but every now and then we do catch a death of a star. They're very, very bright. I mean, you can see them from Earth without a telescope, anything like that. That being blasted outward, and it'll stay bright for months, and then it'll begin to fade over time. But the rate at which it fades kind of helps the astronomers model what kind of death throw exactly it was going through. So they do look at those rates. And that'll become important when we talk about the cosmos as a whole, the universe as a whole. We'll think about this again in there. But yeah, so the explosion, collapsing of the core, but yet the explosion of the outer part of that. And so a couple types in here. Of course, the type 2 is just a very massive star using its nuclear fuel to iron and then exploding, right? A type 1 is the one where it's an explosion when the mass is transferred to a white dwarf and we exceed the Chandrasekhar limit of that 1.4 solar masses, which of course is the minimum mass of a white dwarf. And that causes it to collapse and fuse its remaining nuclear fuel. So when we think of the type 1, it's usually got the white dwarf, okay, and a massive star kind of thing. But yeah, so just a couple of variations of these just cataclysmic explosions. I think they're going to have some pictures there. So type 1a supernova, when a white dwarf in a binary system that we just talked about receives enough mass to exceed the Chandrasekhar limit and then go ahead and collapse with these. So very compact objects result from these. Okay, let's see, they're I think going to take you through some scenarios, but of course that white dwarf would be entirely destroyed. So The less common one is believed to occur when a massive star in a binary system loses its outer kind of layers to its companion star. It could develop maybe an iron core and collapse, producing a supernova in there. But they're kind of looking at the fastest computers and trying to do some modern theories to understand these explosions. But they have witnessed some. This was from AD 1054, where the Chinese observed and wrote about this one. And seeing sort of this remnant kind of glow, so a supernova remnant, where the glow is produced by synchrotron radiation, so spiraling through a magnetic field sort of thing. Electromagnetic radiation gets produced by the spiraling through this magnetic field. This beautiful glow, gorgeous colors with that as well. But synchrotron radiation, these magnetic fields that the gas is sort of getting spiraling through. The electrons are spiraling through that. There we go. A blue glow of synchrotron radiation happening. Sort of electrons are spiraling through a magnetic field, creating this beautiful bluish kind of glow there. So a supernova kind of remnant that we can observe. Okay. Yeah, there was one. Here's one. 1987. This was the star to begin with. Okay, the part of the sky with the star in it. And here's a supernova. Just look how large that got, how luminous that got. That's an extremely powerful explosion to go from like this on the sky to like that. So they do every now and then get lucky. They're pretty rare, so it's a matter of whatever part of the sky you happen to be studying in your career, right? If you get lucky and you happen to see the supernova, because they're rare and we don't really know when a star is going to go through a supernova explosion sort of thing. So sometimes we do get lucky. Okay. Well, and they're just talking about the light curves on your supernova. So they do get very, very bright, and then they start to fade over time. And so here we've got the type 1 and how they fade over time, and then the type 2 and how they fade over time. And so they're trying to compare those different types to whatever supernova they happen to actually get to observe, and try to distinguish and put them into a particular type of supernova. So just some research in the supernova remnants, just some gorgeous pictures to observe there with that. Okay, so we've got our stars, massive stars, exploding into supernova. Okay. And depending on that remnant, what's left over with that core of the remnant, depending on what the mass is for that, we can get a couple varieties of compact objects that we talk about. So yes, gravity always wins, right? So the theory is going to predict that the star must eventually die, and when it dies, it's going to leave behind one of these three final types of remnants, these compact objects. And we've already talked about the white dwarfs, that they have contracted down so much that their pressure is actually degenerate electron pressure. So the electrons don't want to come together, and so that's as contracted and compact as it can get. So it's being sort of supported by that degenerate electron matter pressure. Okay, a white dwarf is, and so it really can't get any closer than that. Now, and that'd be, you know, less than 1.4 solar masses for a white dwarf. Okay, well, a couple other ones on here. We've got the neutron star and the black hole. Okay, very compact objects. Your neutron star, if your core that's left behind after the supernova is between 1.4 and 3 solar masses, we're going to get what we call then the neutron star. And if that core, the leftover remnant of the core after a supernova explosion, is greater than 3 solar masses, we call that a black hole. So depending on what happens, these are very compact objects, depending on their masses, we'll get a couple of varieties in there. So very high density final states here, and we'll look at these last two, the neutron star and the black hole. So neutron stars, a little over a solar mass, right? Not much more than a solar mass, compressed into a very small radius of only about 10 kilometers, okay? So its density so high, okay, that the matter is only stable as this pure kind of neutrons. So now it's become so compressed, okay, that the protons and the electrons are kind of fused and form what we call neutrons, right? Proton, these are neutral charges, little particles, pure neutrons. So that's why it's called the neutron stars for this category. So do neutron stars actually exist? How can we get something as dense as that? And so they've done some studies, and their physicists are predicting that, well, these neutron stars should spin very much like electrons do, and a gas of neutrons could become degenerate and therefore nearly incompressible. So they do think that these do exist, and they're sort of predicting that they should spin very rapidly. Okay, perhaps 100 to 1,000 rotations per second, that they should be very, very hot, temperatures of millions of degrees Kelvin, and have a very strong magnetic field. So theoretically, they've kind of predicted what these should behave like. And so a lot stronger, a trillion times stronger than the Earth's or the sun's or even the Earth's magnetic field. So extremely strong magnetic fields for these. Okay. So the collapse of a massive star's core would greatly increase its spin rate by conserving the angular kind of momentum and get it to spin during this. So creating a really strong magnetic field happening at a very high temperature with these. So physics kind of theoretically predicts these neutron stars, but what about, the actual kind of observation of these? And so a lady, Jocelyn Bell, in 1967, she was a graduate student, found some peculiar kind of pattern in the data from a radio telescope that she was studying. And she really just thought, this is so precise and repeats. And so it's just a series of these regular pulses. It was unlike any, other radio signals from other celestial bodies, but they found it day after day. That same celestial latitude and longitude, and so clearly it was celestial in origin. And so yes, this pulsing kind of a star, they called it a pulsar, pulsing star, pulsar. They kind of combined those names. But Jocelyn Bell was the graduate student at Cambridge that was studying this in 1967. So she was the first to really discover these pulsars, which turned out to be neutron stars. Actually, at first, it's kind of silly, they kind of considered naming it the LGM, or Little Green Men, thinking that this was coming from an intelligent alien Little Green Men civilization kind of a signal, but they dropped that name in favor for pulsar, so a contraction of pulsing star, so a pulsar. And so she had observed with her radio telescope was the first known pulsar. Okay. Now, her professor that she was working under, Hewish, received the Nobel Prize in Physics for this. But she has seemed to be remarkably gracious about it. We all know it was Jocelyn Bell that discovered it, so we'll give her the credit. He can have his Nobel Prize. Yeah, we know who did it though. So anyway, these pulses, so 0.00 seconds, lasting, very, very short term on some of them. But this was very exciting that they discovered these pulsars. And so they liken it, or an analogy of it is to a lighthouse. So the rotation of the lighthouse as the beams kind of come around. And so these pulses of what we're seeing, we've got this magnetic axis of the neutron star right here. Okay, it's kind of inclined in its axis of rotation. I mean, Earth is inclined in its axis of rotation as well. But as it's spinning around, like predicted, spinning, every now and then that beam of rays kind of come right towards the Earth and those pulses that she was observing. So they do kind of liken it to this lighthouse spinning kind of around. But the beam could point roughly towards the Earth and we would detect a pulse. And then while it was neither pointed towards the Earth, you wouldn't detect it. And so the spinning was giving this precise kind of pulse of energy and known as a pulsar. Okay, bursts of radio waves because the star was spinning. The neutron star, they called that. Okay, and physics did kind of predict that, but she actually was the one, Jocelyn Bell, that did discover those. Let's see, they're going to just talk about different, trying to kind of show what types of evidence there is for things like this. But if you've got a neutron star with a companion of another star, so a binary pair of stars, and one of them's kind of your neutron star, well, remember how as they're evolving, right, a little bit of that mass can get accreted onto the neutron star, and we can get some X-ray beams that could come from that, because that gets really hot around the accretion disk there. Okay, and so yeah, you can get some X-rays coming off of these, and so they found and detected some of those potential objects that they think are actually the neutron stars, and Hercules X1 is thought to be a pulsar or a neutron star in there, and so that's, and they've got several other options in there. But the gravity, okay, so Einstein's general theory of relativity is describing gravity as curvature of space-time. So space-time, you got space that's kind of a three-dimensional thing, and time is like the fourth dimension. That's like the fabric of the universe. And so Einstein's theory is saying that gravity tells space-time how to curve, and then that curvature of space-time tells matter how to behave, kind of thing, around it. And so the sort of the curvature of space-time, that any rapid change in gravitational field should spread outward at the speed of light, known as gravitational kind of radiation. But that because the stars are gradually spiraling toward each other, okay, they radiate orbital energy away, okay, with my screen, as gravitational radiation. And so their work with these binary pulsars gave them a Nobel Prize as well, Taylor and Hulse, their work. But short bursts of millisecond pulsars, so they do have a variety that they're talking about in here. And the interesting thing is they've actually found some evidence that you can have maybe some planets orbiting a neutron star. So that's what this one's talking about, that there might be some planet-like masses that are, 4 to 3 Earth masses that were actually orbiting the neutron stars. So that's kind of an interesting thing that they found. But all of these are pertaining to the neutron stars. So that degenerate kind of neutron pressure is what's keeping that object from completely collapsing. Okay, and so that had to do with supernova remnant between 1.4 and 3 solar masses for that core left over. We think that becomes what we call the very compact object of a neutron star. Well, the black holes are, got your supernova remnant, and the leftover core of that is greater than 3 solar masses. And so for that one, it's hard to imagine these black hole massive objects these are, and these are stellar black holes. We have things that we call supermassive black holes that are actually in the cores or centers of galaxies, but this is a stellar black hole that they're referring to. But to try to predict these, they were thinking, well, how fast must an object travel to escape the surface of a celestial body? You know, neutron stars are kind of, you know, we've had a little success with that, but the quest for black holes has met some success with this. But how can something be so compact and yet so massive? Okay, is what they were trying to think about for our black holes. I can get the screen to cooperate. It's getting tired, I think. Okay, so escape velocity, they're talking about, because with our black holes, they are so massive and so compact that light, things traveling the speed of light, can't even escape from them. And so they're talking about the escape velocity of an object. Okay, depends on the mass of the celestial object and the distance from the center of the mass. Okay, so if a celestial body has a large mass, its gravity is strong, and you need a high velocity to escape from the surface of it. So thinking about a black hole, okay, yes, they're going to really have a strong gravitational field around them, but you've got to get close enough to it. They're not going around like a vacuum cleaner sucking up everything, you know, in the universe. You actually have to be close enough to it, okay, to get the effect of the black hole. So it's a matter of how close you're getting to it, and then electromagnetic radiation cannot escape from it, is what they're kind of talking about, the escape velocity on there. Okay, so you get an object massive enough or small enough, you could have a escape velocity that's greater than the speed of light, which means electromagnetic radiation cannot escape from it, and nothing travels faster than the speed of light. So photons are unable to escape from it. So you're thinking, well, how can we detect them if we can't see any light coming out of them, right? But we do have some good ways to look at them, because when you get something close to such a massive object, it's going to behave strangely. It's going to start moving much more rapidly, and to the point that it could kind of give you some X-ray beams coming off of it. So we can't really see the interior part where the black hole is, but around the black hole you can observe. So here's the core. If it's collapsing and it has a core that's 3 solar masses or above, well, no force can stop, that collapse. Not electron degenerate pressure, like in our white dwarfs, not the degenerate neutron pressure of our neutron stars. So nothing can stop that from collapsing all the way in, okay, to what we call this point of singularity. Okay, 0 radius. It's really hard to kind of think about it, and its density becomes infinite. So it's this massive, compact kind of object. So it's really difficult to think about that 0 kind of radius, okay, around it. But that's sort of what the black hole is referring to. And it's referring to the volume of space, not just that singularity, but a volume of space around the region's center. That's the black hole, okay? So it's contracted so small that the escape velocity is so large that, you know, it's greater than the speed of light. So no light can escape from it. You can't receive any information. How can we study it, right? About the object or the region kind of right near it. But just far enough out, and we can study what happens to matter as it gets close to that. And so there was Einstein's theory again, where it's treating space and time as a single kind of entity called space-time. And gravity kind of is described as the curvature of space-time, okay? So when you get towards a very massive object like a black hole, things are going to behave gravitationally differently as it gets towards it. So observing just outside of sort of this event horizon, they call it the sphere of volume around the black hole, looking at the behavior of things as it gets near that very massive object, yeah, you're going to see gravity affecting that. So Schwarzschild was a gentleman that did a lot of work on this, and so they do kind of have the radius of this event horizon named after Schwarzschild. Yeah, he's kind of went through some of the theory work on a black hole, so the Schwarzschild's black hole. But the event horizon, right here, sort of this event horizon around the black hole, so it's the boundary between this isolated volume of space-time called the black hole and everything else in the universe, right? So the event horizon right there, okay, and then singularity, that zero radius, which is just unimaginable, zero radius, how compact that is. But right here, so the radius of the event horizon is known as the Schwarzschild radius. So R subscript S, Schwarzschild radius. So this is the radius within which an object must shrink to become a black hole, and the point of no return for any object that might be falling in later. So radius within what an object must shrink is the Schwarzschild radius, they call that. And a point of no return for anything that happens to kind of get that close. Okay, so the event horizon has a radius that's equal to the Schwarzschild radius in there. So that's the size of the black hole. It's Schwarzschild kind of radius and proportional to its mass. Okay, so they kind of talk about how, yeah, it's a misconception that black holes go around sucking up everything like giant vacuum cleaners in the universe, but it's just a gravitational field, and if you're far enough away, Newton's law kind of told us this way back in, what was that, chapter 3, about the inverse square law. So the farther apart two objects are, okay, the distance squared, your force of gravity becomes less, right? It's an inverse relationship. So the greater your distance is, the smaller the effect of that gravity. So it's at a very large distance, well, its gravity is no greater than that of any other normal kind of size mass. So if the sun were replaced with the one solar mass of a black hole, the planets and the orbits, nothing would change, right? You've got to be close enough in for it to be any kind of an issue. Okay, so what they've kind of got is sort of the look at what a gravitational field around a 5 solar mass black hole is. So it's sort of really curving, almost like it says they're kind of like funneled, but in this picture, but it's more of a spheroid, a sphere around it that any sort of electromagnetic radiation, stars that get close to it kind of thing. It's almost curved back on itself. Space-time has curved back in on itself in this spheroid kind of shape, and nothing else can get out of that. Okay, once it's gotten in, we can't get any sort of information back out of that. But they're kind of take a leap into a black hole here, is what they're talking about, and saying that here we are leaping into the black hole, okay, and you're about 1 AU away from it. The gravitational pull wouldn't be very great at that point, right, because you're pretty far away. And the longer you fell, the closer you came to the center, the faster you travel. Your wristwatch would show that you fell for about 2 months before you even reached the event horizon, okay? And so as you continue to go here, your friends would never actually see you cross the event horizon. To them, you just fall more and more slowly, but you are actually getting into it, right? And then here you are, you notice no effect as you fell toward the black hole. Your friends would need to observe at longer and longer wavelengths to actually detect you because of this gravitational redshift, right, to longer wavelengths. So in order to actually see you, they might need to look at you through infrared radiation wavelengths. But here you are, if you're falling feet first, you're going to get really stretched as you do this. But your feet are going to be closest to the event horizon of the black hole. You feel your feet, okay, being pulled in more strongly than your head would be, okay? And as you fell closer, become even stronger. And another force would be compressing you. You're going to get spaghettified. Spaghettification is kind of a term that they use. But your left side, your right side, you know, getting compressed and you're getting stretched. I think they have a little picture. Yeah, so really getting stretched as you're going through this black hole kind of thing. And so in sci-fi movies, they think, oh, let's just travel through a black hole and pop out somewhere else in the universe. This is not a feasible means of transportation because they're saying, needless to say, this would render you inoperative as a thoughtful observer, getting stretched like that. And I think somewhere along the line they'd say, and at the very least you would lose your luggage if you tried to travel this way. So this book's kind of silly, but not a good way to travel in the universe. Yeah, science fiction tries to make that, and it makes for good science fiction and good movies like that. But so a black hole, we need to look for some sources of X-rays that might be coming from that matter that's just about to enter that event horizon. So it's gotten close enough now that it's going to begin to behave differently and start moving much more rapidly because it's getting in on stronger and stronger gravitational field as it gets closer and closer. Not that it's past the event horizon, because then we can no longer get any information out. But as it does get in and around the event horizon, we can take a look at that, and we would end up looking for a source of X-rays coming from that just before disappearing before that event horizon. And so they have had some good luck in searching for black holes, in that you want it a star that's in a binary pair with a very compact object greater than 3 solar masses, right? That has these X-ray binaries. I mean, we can't actually see the black hole, but we can see the behavior of the matter right around it, emitting X-rays, right? As much as a binary containing a black hole should, okay? So they've actually, you know, got some good evidence, good candidates of what these black holes might be, okay? So some matter kind of entering the hot accretion disk around that hot object. Of course, we can't see anything towards the center of it. No information's coming out of that. But again, so we're getting a little bit of this supergiant companion with it, some of the material from that. So these binary companions, right? With a very compact object here, and if you get the X-rays coming from that, you've got a good potential that that's a black hole. So the search for black holes has, given us some good success. You're looking for X-ray binaries coming off of a very compact companion of greater than 3 solar masses in that. So the binary companion stars. Good success with that, and I think there was a list of potential, here they are, potential black hole kind of candidates. This table is probably a little old too. They've probably even added more to our list. What their companion star is, so a supergiant here, a main sequence star, supergiant there, but that they're in a binary system, orbiting one another, and the compact object is greater than 3 solar masses, and you're getting all these X-rays coming off of it around the event horizon. So that's met with some good success in trying to find the black holes. Okay, so I think they're just kind of going through. So whether the compact object is a black hole or a neutron star, okay, it will depend on what the mass of that core is in that compact with the companion there. They do have, strong gravitational fields. Both of those very compact objects do. And so it would be coming down to the amount of mass that that companion star has. Whether you're seeing the pulsar, periodic pulsing of X-rays, or you've got a much more massive one and you're seeing X-rays coming off of that. So mass would kind of depend on whether you have a neutron star or a black hole. Okay, but very, very compact objects. They're talking about gamma rays coming off of some of these as well. So the Compton Gamma Ray Observatory took a look at that as well, detecting some gamma ray bursts as well. So yes, trying to determine if they are neutron stars or black holes. So that's kind of in summary. We'll pop this back under the screen again. I don't know how well that's showing up. But beginning, with whatever your star's beginning mass was, we do see from our summary the various death results, okay, as our stars do use up all their fuel, right? And then they go through various death throes, all depending on what their beginning mass was. So whether we're getting, just a white dwarf sort of a thing, whether we're going ahead and swelling into the red giant phase and maybe getting a planetary nebula, expelling the outer gas as we go, and then compacting down to a white dwarf stage, something like this, what the sun could potentially do. And then way over here, what maybe a more massive star might end up doing. So a couple scenarios in there. Here we had very massive stars, greater than 4 solar masses, becoming supergiants, and then explosions, supernova explosions, type 1, type 2 kind of thing, very massive stars exploding. Okay, and then possibly like the type 1 was where you had stars in a binary system, and some of that mass got put onto a white dwarf sort of thing happening. So various types of supernova that can happen in our Death Stars. And then depending on the remnant left over the compact object, its core mass size, are we getting a neutron star or are we getting a black hole? Much more massive compact object with a black hole. So variety of stars, and really their deaths depended on just how much of beginning mass did they have. So this is a nice little figure that summarizes what we've talked about today. So We've taken you through our star unit, my favorite unit, where we first off took a look at the sun, kind of our reference. Then we moved to chapters 9, 10, and 11, where we took a look at the properties of the stars, the formation and star structures, internal look at them, birthed our stars, saw how they lived on the main sequence the majority of their life, and then the various death throes with the deaths of our stars. And so that does complete our star unit. Again, you have several bullets on your study guide that if you have any trouble with any of those, make sure that you get with me so you have a good set of information to study for the exam on. And so I hope you enjoyed it as much as I did. And the what are we? We are stardust. Very appropriate. So the elements that get cooked up in the stars and then get spewed out into the universe, definitely we are stardust. And so until next time, we'll be talking about galaxies next time. I will see you then. Bye-bye.